So welcome everyone. Uh, so today we have presenting his work. Seunghoon has been with us at the Center for Automotive Research for now almost 1 year. And we started to discuss this collaboration almost at the same time last year. And since then, he has been a GRA here at the center, and together we have been working on a project funded by Caterpillar. So the project is not finished yet. We will have other few months likely for us to continue. We had actually to extend the project because more things to do. But in the meantime, Seunghoon is getting ready for graduation, and so will be defending his thesis on Thursday as well. So a little bit a stressful week for a lot of things to do. So Seunghoon is gaining his degree in electrical engineering, his master. He has already a degree in electrical engineering, bachelor from his hometown, and he comes from South Korea. And after his bachelor, he has been working for around 10 years in the field of power electronics. So he has a lot of experience in manufacturing and testing and validating this system. And so we are now stepping a little bit more into the research. And this presentation here is comparative analysis of modular high voltage power electronics architecture for fuel cells and batteries. So Seunghoon, the floor is yours.
Hello everyone. Thank you for attending in this time. Yes, my research title is comparative analysis of modular high voltage power electronics architecture for using fuel cell and batteries. Yes, the table of contents are as follows: introduction and motivation, technical modeling framework, EMS control, and according to EMS control simulation, I will introduce the efficiency map and technical economic analysis. Finally, I will conclude the video. First, introduction and motivation. As renewable energy sources such as solar and wind continue to grow worldwide, from the power systems are facing increasing intermittency and output fluctuations. So these variations cause the issues like working instability and power imbalance, which increase the need for support from battery energy storage system BESS and the port cells. So batteries have stabilized short-term fluctuations with a fast response. However, port cells provide steady, long-duration power, improving overall power quality. At the same time, the power grid is shifting from a centralized to distributed structure, making flexible and power electronic-based interface essential for targeting diverse energy sources. So, as a result, it has become key components that determine the stability, efficiency, and the reliability of the entire power systems. Yes, the battery is an electrochemical storage device with very fast output response, making it ideal for handling sudden load changes. In contrast, the port cell is an electrochemical energy source that responds more slowly, however, provides low duration and stable power generation. The comparison table on the right clearly shows their contrasting characteristics. Post cells offer continuous operation as long as power is supplied. However, they have low energy storage capability and reliability, uh, relatively, relatively low efficiency, around 60%. On the other hand, batteries have high energy storage capacity, extremely fast response, and high efficiency near 98%. When these two are combined, the hybrid system leverages the strengths of both. The battery manages fast transients, while the fuel cell provides a long-term steady energy. So this improves overall stability, efficiency, and power quality, making the fuel cell battery hybrid system highly effective solution for application requiring high power and high reliability. So this slide summarizes the key motivations behind studying fuel cell and battery hybrid systems. First, fuel cells and batteries offer complementary strengths. When combined, they can achieve fast dynamic response, high power capability, long duration operation, and improved overall efficiency. For this reason, fuel cell and battery hybrid systems are already being explored in both automotive applications and grid practice systems. Another motivation is the opportunity to deliver more stable, reliable, and optimize the power across the modern energy systems. However, several challenges remain. System integration is complex, and additional efficiency losses introduced by power electronics must be considered. Moreover, designing an effective energy management strategy is essential to coordinate the power flow between the two sources. Therefore, this research focuses on addressing these challenges, specifically identifying how fuel cells and batteries should be combined, determining which power electronics architecture are most efficient, and developing optimal energy management approaches for hybrid systems. In most configurations, the ESS converter couples multiple energy sources and performs the necessary DC to AC conversion before delivering power to the grid. Power is then passed through a grid interface transformer and protective switchgear, automatically supplying the AC grid and the connected load. So the table at the bottom summarizes the wide variety of converter topologies that can be used for ESS applications. So these range from traditional DC-to-AC inverters, such as two-level voltage source inverter, current source inverter, and conventional H-bridge inverter. For higher power applications, multi-level converters like MPC, CHV, and MMC are commonly adopted. The less noted and isolated converters such as DAB, SLC, and multiple active bridges are also frequently proposed in literature. So overall, the ESS to grid interface provides many converter options, and selecting the right topology depends heavily on system requirements such as efficiency, voltage capability, quality, and reliability. So this slide compares several control of common disk configuration. And yes, the first configuration, no coupling, simply pairs the storage unit. This approach only works when the units have identical voltage and characteristics. And the second option is using an individual these two AC motors. Each storage unit connects to the AC pulse through its own inverter, allowing units with different voltage levels and capacities to operate simultaneously. This supports the excellent flexibility and scalability, however, at the cost of increased system and complexity, higher hardware requirements. More efficient approach is N-1 these converters with just one these two AC inverter structure. Only the storage device that require voltage conditioning use is to these DC to DC converters, while are connected directly to the DC link. This reduces converter size, cost, and system footprint. The final configuration and these two DC converters and one these two AC inverter. It gives poor controllability. Each storage unit is processed through its own DC to DC converter, making it suitable for systems with highly dissimilar storage technologies. Although it provides the highest level of flexibility, it increases losses and overall system cost. Ultimately, selecting the right disk-link architecture involves balancing flexibility, efficiency cost, and the system complexity based on the application's specific requirements. Yeah, this slide illustrates the fundamental differences between AC coupling and disk coupling architectures. So on the left, the AC coupling architecture connects each storage system, such as battery and power cell, to the AC grid, so its own dedicated disk to AC inverter. This makes the system simple to configure and allows different sources with unmatched voltage or characteristics to operate independently. On the right, this coupling architecture first combines our ESS units into common disk bus before using a single disk to AC inverter to interface with the grid. In this configuration, the sources are coordinated at the DC level, and only one AC conversion stage is required. This generally improves overall efficiency and enables more optimized energy management between the battery and power cell. So in summary, AC coupling provides simplicity and independence, while this coupling offers higher efficiency and better integrated control. So in this coupling approach, multiple ESS units share a common disk bus and use a single display AC inverter. This allows for centralized voltage regulation and power flow management at the DC level, improving overall conversion efficiency. The common disposal also enhances modularity, making it easier to add or replace energy storage units. However, this coupling typically requires these two DC converters for voltage matching and additional conversion stages may introduce efficiency losses. On the other hand, AC coupling uses individual DC to AC inverters for each ESS. This allows each storage device to operate independently and simplifies the expansion because each inverter can be sized or selected based on its own characteristics. The downside is that multiple AC conversions can reduce efficiency, and coordinating several ESS units on the AC side requires more complex synchronization and control. So ultimately, some of these metrics are easy to identify as a positive or negative feature, while other require operational considerations. Yes, so this slide explains the motivation and necessity behind this research. Although both AC coupling and discoupling architectures are widely used in power electronics industry, the duality between them has not been fully explored. Most existing studies focus on improving performance within a single architecture, either AC or DC. However, the coupling structure has a major impact on system efficiency, losses, control complexity, and overall operation. So despite this, there is no standardized criterion for selecting the optimal architecture. Only a few recent studies have compared AC and DC coupling, and even those focus mainly on electrical performance without considering system level implications. For hybrid systems like fuel cell and battery combination, both technical and economic aspects must be evaluated together. And this integrated perspective is becoming increasingly necessary. So the primary goal of this research is to systematically analyze the technical and economic trade-off between AC and DC coupling architectures. Yeah, the scope of research. The first is comparative analysis of AC and DC coupling architecture for using fuel cell and battery hybrid systems. Two, evaluation of power flow, loss mechanisms, and efficiency characteristics of each coupling topologies. Three, comparison of control and EMS behaviors, emphasizing structural and operational differences. For establishment of technical design criteria for components, topologies, and operation in fuel cell and battery hybrid systems. Finally, derivation of architecture selection guidelines for high power, high efficiency hybrid energy systems. This slide presents the overall approach used in this research. The first step involves architecture design, where both AC and DC coupling architectures are developed, components are sized, and system models are built using appropriate computer topologies. The second step is verification through simulation, MATLAB Simulink. Using MATLAB Simulink, the study models the power flow control algorithm and loss mechanisms for each architecture, enabling evaluation of the realistic operation scenarios. The third step consists of two parallel evaluations, technical and economic analysis. Technical analysis examines efficiency, power loss, THD, battery cycling, and grid dependence, energy autonomy, and load satisfaction. And the economic analysis is consisting of CapEx, OpEx, SOE payback, and NPV ROI. This combined assessment reveals which architecture offers the best performance and economic value for fuel-cell battery hybrid systems. These are technical and economic metrics. These tables shows the definition and each formula regarding technical and economic metrics. Yes, so this slide shows the complete flow chart used for the integrated technical and economic analysis. The process begins with system architecture design and sizing, followed by detailed simulation steps, including converter models and load profiles. After running simulations for defined duration, data such as power flow, losses, and operational behavior are extracted. These results are then used for two types of evaluation: quasi-static evaluation and dynamic evaluation. Once the technical metrics are compiled, economic evaluation is performed including CapEx, OpEx, SOE, NPV, and ROI. These assesses the financial viability of each coupling architecture. Finally, the technical and the economic results are combined to produce a comprehensive comparison between AC and DC architectures. Overall, this flowchart illustrates structure and holistic framework that integrates technical simulation and economic modeling to support the informed architecture selection. Yes, this slide summarizes the three key modeling tools used in this research: dynamic modeling, quasi-static, and map-based modeling. Dynamic modeling is the most detailed representations capturing for switching behavior, including voltage and current waveforms, switching and conduction losses, and pH. It provides the highest fidelity, but requires to have computational resources, so making it unsuitable for low-term or system-level simulations. The quantitative model removes fast dynamic, but provides accurate averaged behavior with significantly reduce the computation time. It offers a good balance between accuracy and speed, making it ideal for portrait level analysis, efficiency estimation, and generating performance maps. Finally, the map-based model is the simplest and the fastest approach. It does not model voltages or current directly, but relies on pre-generated efficiency or power maps. This enables large-scale system simulation, EMS optimization, and economic evaluation. However, its accuracy depends heavily on prior models and it cannot capture detailed electrical behavior. By combining these three modeling approaches, this research ensures both high accuracy in component level design and high efficiency in system level technical and economic analysis. The next is technical modeling framework, design, sizing, and control. This slide briefly shows commercial examples of AC and DC coupling systems. On the left, companies like Tesla, SMA, and Schneider offer AC coupled solutions. On the other hand, the right, SolarEdge, Dynapower, and Hitachi Energy provide DC coupled products, which are typically used in high efficiency DC power systems. These examples illustrate that both coupling methods are widely adopted in the market. So this slide provides a summary of the state of commercial components used in full-cell batteries, these two AC motor and these converters. The table compares key specifications such as rated power, voltage range, efficiency, and operational characteristics. And these products were chosen due to their high power capability, strong efficiency, performance, and suitability for full-cell battery hybrid applications. For these tables illustrate the available commercial technologies and identify which components are most appropriate for the system architecture analyzed in this research. Yes, the output voltage. This is system specifications in my research. The output voltage is three-phase 480 volts. Current is about 600 ampere RMS. Output power is maximum 500 kilowatt. And control method is the DQ current control and single phase shift modulation method. The DQ current control is related to the VSI DC to AC motor control method. The SPS single phase modulation control is related to the EAB DC to DC converters control method. And system efficiency is more than 95%, and output voltage and current TH value is less than 5 and 8%. It is used for standard of IEEE 519. So for this design, the inverters are configured in two 50 kilowatts of building blocks with safety margin of 1.2 times voltage and 1.5 current, 1.5 times current applied to meet device and summer limits. The DC voltage is selected in the from 700 to 800 voltage range to support 480 AC voltage grid, and the air filter are sized to satisfy the THD requirement of less than 5%. The control strategy is based on DQ current control, where the D-axis regulates active power and the Q-axis regulates reactive power. Grid synchronization is performed using PLA-based control, and both the full-cell inverter and battery inverter operate independently while connecting to the common AC source. From EMS perspective, both sources can supply active power, but the full-cell provides the steady base load while the battery offers a fast dynamic response and peak power support. So this configuration highlights the simplicity and independence that characterize these coupling systems. So similar presentation, this slide describes the design process and control strategy for DC coupling architecture. Yes, design process is almost the same, and control strategy is almost the same. However, the difference is just the DC coupling architecture include DC to DC converter DAB. So the control method and the SPS control method. So regarding the EMS, it distributes the power among full-cell and battery VSI based on DC conditions. It continuously recalculates power responses using proportional constants such as the K factor to maintain consistency with AC coupling. The study assumes unit power factor, so reactive power control is not included. This architecture allows power management to be consolidated at the DC stage, improving efficiency and enabling high power operation. So the fundamental principle, power balance in hybrid energy systems. So this power balance equation is needed by the related to EMS control method. So the fundamental principle is the law of energy conservation, meaning that the total supply power must equal the total consumed power at all times. Mathematically, the sum of the full-cell power, battery power, and grid power must match the load power. So as a result, the EMS ensures real-time coordination to maintain power balance, satisfy load demand, and keep the system stable under various operating conditions. This slide explains why post-split between post cell and battery is essential and what makes it challenging. Because post cells and batteries have fundamentally different characteristics, they cannot be operated effectively without coordinated power management. Post cells deliver steady long duration power, but respond slowly, whereas batteries provide fast transients and peak support. Therefore, proper power sharing directly influences system efficiency, stability, reliability, and lifetime. However, power split introduces several challenges. Dynamic mismatch between the two sources, battery SOC management, fossil lamp plate limits, couple interactions, and some load variations. These factors significantly increase the complexity of EMS control. So the EMS allocates the base power to the post cell and assigns transient and peak power to the battery. So this slide compares the control design of ASD coupling and this coupling architecture. Well, in summary, this coupling offers greater control flexibility and performance, however, at the cost of much higher control complexity compared to AC coupling. Yes, so EMS verification. Yes, so this graph illustrates how the EMS control power sharing between post cell and battery in the AC coupling architecture. In the initial phase, when the load is applied, the battery responds immediately and supplies most of the required power. The VSI limits the battery output to 250 kilowatts as the post cell starts from a low level and contributes very little during the initial transit. In the step 2, the post cell begins its ramp up. Since the post cell has a slow dynamic response, the battery continues to supply the remaining power during this transition. Step 3, the post cell power becomes fixed and the battery follows the remaining load variations. As shown in the graph, whenever the load increases, the battery power rises, and when the load decreases, the battery output is reduced. EMS ensures that the post cell never exceeds its maximum rating of 250 kilowatt. So in step 4, fourth condition is triggered by assuming the battery SOC drops below 20%. In this situation, the battery stops supplying the power and the post cell maintains its maximum power. So post cell support the load as much as possible. Overall, the result clearly demonstrates in AC coupling architecture, the battery manages a fast dynamic and load variation, while the post cell provides a steady baseline, so showing the effectiveness of the EMS trade control. Next is the EMS control for DC coupling architecture. The step 1, so when the load is applied, the both the upper and lower batteries supply power typically in half and half split. Step two, the EMS gradually increases the pulsar power according to the proportional constant K factor. And the DAB DC to DC converter begins delivering baseline power to the DC pulse. As the pulsar power rises, the battery power decreases according to satisfy the power balance. So step three, when the load variation occurs, the EMS recalculates the pulsar Laplaces for branches. The batteries provide the immediate response, quickly supplying the increased power while the pulsar follows more slowly and settles into the new operating power point. So finally, in step four, port condition is simulated by the same, assuming that the battery SOC drop below 20%. In this case, the battery stops supplying power and pulsar maintains its maximum output to support the grid as much as possible. Yes, so this slide summarizes the key metrics used to compare the EMS behavior and the two coupling architectures. So the first metric is power balance, and this means stability, which is most fundamental requirement for any hybrid data system. For EMS performance is confirmed by maintaining this balance at all time. Second metric is the dynamic response to load variations. Your systems experience rapid load changes, and the differences between AC and DC coupling become more visible when interaction behavior. Third, conversion efficiency and loss distribution. This coupling involves more power conversion stages, so it can reduce efficiency, whereas coupling typically has fewer stages and therefore achieves a higher efficiency. For battery SOC management stability, it is another critical aspect because SOC is a primary input for EMS decision making. So, and if the power quality, PhD, etc. Since each architecture requires different filtering efforts to meet grid standard. So finally, cost metrics. So the cost metrics such as electricity costs derived from simulation results. It is included to support economic comparison. This allows the study to overcome the limitation of previous work, which of compare architecture only one technical performance.
We need to speed up a little bit here on this side.
Yes, these are the AC coupling and DC coupling and DC coupling architecture diagrams with control method. So in the AC coupling architecture, it includes the EMS control and the DC power control or DC current control. On the other hand, the DC coupling architecture is EMS control and the same EQ current control, however, for controlling the DC to DC converter DAV. So it used the PI control and the SPS control method. So I would like to pursue this explanation. This efficiency map analysis is essential, very essential because it quantifies how efficiency varies under real operating conditions. So efficiency depends mainly on the operating voltage, current level, and the power split between poster and battery. Lower battery SOC reduce its voltage, which increases current for the same power, and therefore increases our conduction and switching losses. The conductor losses are functions of voltage and current because switching losses scale with both and conduction losses scale with the scale of current. So system losses vary strongly with SOC, distinct voltage and power. This slide presents the efficiency map result for the battery and poster power electrics in AC coupling architecture. So, overall, the key variables efficiency in AC coupling are the SOC dependent voltage behavior of the battery, the current increase associated with higher power, and the process current voltage characteristics. These maps form a fundamental basis for later analysis of losses and architectural components. The next is the efficiency map result for DC coupling architecture. The left result is related to using only battery and the right is related to the post cell 100% operation. So in summary, this coupling efficiency is strongly governed by the SOC voltage characteristics of the battery and the power dependent current stress and the process current voltage behavior. These maps provide essential input data for the upcoming loss analysis and system level architecture comparison. These results are related to another scenario for DC coupling architecture. In previous result is only 100% operation of each battery and post cell. However, the next scenario is the combination between post cell and battery. Power splits is 50 versus 50. So overall, this 50 to 50 scenario demonstrates that this link voltage stabilization keeps the input condition for both the VSI and DAV nearly constant, which means their efficiency curves remain similar to the baseline case despite the different power sharing related. So This slide summarizes the main conclusions and key insights obtained from the efficiency map analysis. So the visual story of the efficiency maps, the architecture differences originates from the post-cell conversion chain, the battery. The high system efficiency occurs when post-cell and battery share the load 50 to 50 combination. And batteries SOC 80 to 20% is the optimal operating region for the battery, and efficiency maps provide the quantitative foundation for system design, control, and technical economy analysis. So the next is the necessity of the detailed efficiency maps. The efficiency map provides the quantitative basis for selecting AC and DC coupling architecture and critical for converter sizing, zonal design, and switching strategy. So it is essential for EMS optimization, power split, SOC window, lamp management of battery and water cell. Yeah, so I think
this is a four. So you would like to get to some questions. So we may need to really provide a high-level summary here of this part. We will not have time to go through all the slides.
Yes, in short, I calculated technical and economic analysis for by using technical 7 technical metrics and 6 economic metrics. So yeah, as a result, the both architectures need more technical requirements, and although the structural architectures differ, their operational performance is highly comparable. To calculate the economy analysis metrics, so I assumed some metrics. For example, electricity price is 0.154 in Ohio State standard, and operating hour is just 1 year. So, and discount rate analysis period is 5% and 10 years. These are almost the same industrial standard. And material, labor, and overhead expenses cost amount based on my experience managing 200 kilowatt system project. The maintenance cost is calculated using the CapEx cost by 5%. The rated capacity, the maximum is 5 kilowatt. So and to calculate annual electricity capacity, I use the technical metrics, so results the efficiency. Yes, so overall, the why both architecture perform similarly in technical metrics. The economic analysis clearly shows the AC coupling provides superior cost efficiency and financial performance. Yes, these are the calculation progress. just finally, finally, I will summarize the key findings and the conclusions of this study. Sorry, we conducted comprehensive technical and economic comparison of AC and DC coupling architectures. AC coupling achieved higher efficiency, lower capex, opex, economy analysis, faster payback period. In contrast, DC coupling showed lower than battery capacity, slightly better THD, and improved isolation reliability. Importantly, both architectures achieve greater than 95% stability, EMS stability and efficiency, and demonstrate strong standalone operational capability. So now the conclusion: AC coupling is optimal for cost-focused and efficiency-driven application, while DC coupling is better suited for isolation required or battery protection applications. So this study provides clear and quantitative design guidelines for selecting hybrid fuel cell battery architecture. Thank you.
So any question here from audience?
Yes. Great work. Congratulations. I would like to ask, at some point you mentioned that you're computing the losses, the power losses online. How exactly are you doing that?
Yes. To calculate and get the result of the power losses, I use the S function block in the battery single link, and I use the voltage, the calculation power loss equations. So in the first, I calculated the power losses in person, and I simulated each power conditions and get the results and compared my calculation result and the simulation result. So
you can mention which kind of components you have considered for your losses. I think that's
oh yeah, so
how did you actually calculate the dynamic losses?
yes.
Losses for the switches, the IGBTs, and other components. How?
Yes,
have a detailed physical model for that.
Yeah, I sized of each architectures, especially BSI and the DAB topologies. So I choose the commercial product, IGBT, MOSFET, inductor, capacitors. So and then I used the real data in their data sets values.
Okay. Which kind of losses did you include?
Yes. For yeah. The first step, when I calculate the AC coupling and DC coupling, in the first place, for AC coupling architectures losses, I get the results of the switch device and capacitor and filter. Of course, you know, the switch device losses divided the conduction loss and the switching loss. On the other hand, the for this coupling architecture, the VSI and air filter is the same. However, it has to include the additional power loss regarding this converter. DAB. DAB has two per bridge section, so and then each per bridge has 4 MOSFET, and DABs has the leakage inductor and transformer. So I calculated additionally MOSFET is switching and conduction loss, leakage inductor loss, and transformers loss. So as a result, for example, VSI, especially its coupling architecture's power loss result is 96.8. But you see coupling architecture's power loss and especially as efficiency result is lower, maybe 96, almost 96. Because of just 1%.
Thank you.
Anything else? No?
I'm kind of power electronics team here. Question?
They can get better answers from Bhagavan. Fine?
If not, I have another question. You've assumed that the power factor is 1, so you disregard the reactive power. How realistic is that assumption in a real system?
Yes. For example, this research is related to using the traditional topologies, especially VSI.
Yeah.
DAB is so great topology as this converter. However, maybe I think MAB or SLC is more greater and better topologies to get higher efficiency and power. So in the real, when I search here for some companies information, some companies use the BSI topologies, almost use BSI topologies, and especially some companies using or utilizing the DC to DC converters, or most companies use just DAB topologies.
Okay, so you're saying that it's not yet implemented in full to actually know what a real system looks like, but if it has power factor of 1 for a real system.
Yes.
It's not.
In the real system, the power factor is 1 is impossible.
Yeah, absolutely. But is it close to a real system like your simulations should be?
Yeah, when I simulated this I just considered the power factor is 1 because I would like to get the ideal results.
Okay.
However, this EMS include the calculating method related to the reactive power.
Mm-hmm.
I just selected the value is just 1 at 0.
Okay, 0, yeah. Okay.
Seunghoon, can you jump back to the slide that had the battery cycling on it?
Cycling?
Yeah. Just want to make sure I read that right. So 28 cycles per day, is that like a full charge discharge cycle?
Yes, this battery cycling is, I consider the efficient battery. The battery's efficiency is calculated and get the result of using the efficient maps above the presentation. Um, So the battery cycling matrix is both architecture, uh, nearly the same values, about 28 cycles per day. So I would like to explain this result may seem surprising same values.
I think the question was more related to the number. Why so many cycles?
Yeah, it was, why is so many cycles when, if you consider like a badge or something, we'll get generally a lot less than one per day.
I see.
Maybe three on a bad day. But how does that impact the cycle aging of your battery? That is a very high number.
I don't think it's
Oh, okay.
It was more seeing if there was any difference, visible difference in the charge efficiency. So it was charging and discharging, charging and discharging. Consider the 500 kilowatt
I got you.
limits.
Okay.
So,
Then I think the maximum power is 250 kilowatt. However, I choose the battery capacity is 250 kilowatt hour, so too low. However, I just design and simulate for a short time, just 1 or 2 seconds.
yeah, but you also have 80% to 20% charge limits, so that's what brings almost 28 instead of 24 in a day. So yes, limit of the numbers of
Yeah.
cases.
Gotcha.
Yeah, thank you. However, please, I have some more. Sorry, I'm sorry. Because I don't understand the 28 battery cycling is higher.
Is that
Sorry, I just calculate the use the emissions.
okay? If there are no more questions, we thank Seunghoon. Here we went a little bit over time. We don't need to adjust.